Hi, this is Russ. I wanted to review hot gas layer patterns from section 6.4.3 of NFPA 921. This is part of a series of videos that help equip individuals with some of the tools that are associated with forensic fire investigation. So this image is really good. It shows a very clear line of demarcation between a cooler boundary on the lower layer and a hotter up and sootier upper boundary. This was a room that would have been adjacent to likely a flashover condition, but it wasn't a flashover room in and of itself. So these kind of rooms have clear indicators of that sit deposition that can help identify or at least point toward other locations. And if you look at it, you can see a little angle on this line of soot, and that typically happens when it points toward a ventilation opening. So upper gas layer patterns, radiant heat flux from hot gases produce damage to surfaces. The process begins as compartment approaches flashover. Lines of demarcation represent a specific smoke layer boundary on vertical surfaces. So take a look at this. Once again, this is not a compartment that reached flashover conditions. You can tell from the furniture and the floor, the furnishings aren't charred, but there's clearly a boundary line. So when you have, there's a theory called the two-layer boundary theory. You have an upper layer of hot gas and a lower layer of cold air. And that's why it's always valuable to, crawl when you're in a fire to avoid that upper layer boundary. And this shows it very clearly. It appears that the window is still intact. Typically, you're always going to have window breakage, up to about 500 degrees Celsius, keeping in mind that flashover is about 1,000 degrees Celsius. So it doesn't look like it got extremely hot in this compartment. Upper layer patterns are difficult to identify after transitioning to ventilation controlled fires due to extensive damage on all surfaces. So if you go back and look at this fire, if you went to a flashover or a ventilation controlled limited fire, what would end up happening is the whole room would basically combust. So the upper gas layer patterns are most valuable, at least this kind of the sooty deposition pattern is only valuable in pre-flashover conditions. The upper layer damage includes lines moving out of ventilation openings and lines of demarcation showing upper smoke layer boundaries. Demarcation lines will usually have uniform level lines of damage unless upper layer is flowing out of an opening. Let's take a look at a compartment fire. This is just a laboratory test. A fire was started in a trash can. You can see that after a certain amount of time, it's actually just a few minutes, but you see a fairly stable lower smoke boundary. And then you see the whole building basically, the very hot fire. You see fires and locations all over the place. But more importantly, look at the floor. You see how it's really smoking hard. A lot of pyrolysis there. This is ready to just explode and flash over. The upper layer of the fire plume contains smoke and particulates at an elevated temperature. When the fire plume is contained in the upper portion of the compartment, the upper gas layer radiates heat to exposed surfaces and affects fire patterns. So once you have about 600 degrees Celsius for an upper layer, this location, it typically is going to radiate about 20 kilowatts per square meter at the floor. And that's the threshold for reasonably quick piloted ignition for combustibles on the floor. So at that point, you're going to see char all over the place, all over the compartment, and that's all going to block the city deposition lines. So here's a definition of plume. You see the flame plume and the fire plume. You see how dark that city smoke is. It should be obvious that city smoke, what it does is it will deposit on the walls, and it does that because of a temperature differential. When the walls are cool, the smoke effectively condenses on the wall surfaces. But if the fire's hot enough, it heats the walls up to a sufficient temperature that condensation can't occur. Soot deposition, incomplete products of combustion resulting from pyrolysis and ventilation limited fires and cooler walls result in soot deposition. Soot deposits higher in elevation due to the two layers, keeping in mind that the upper layer is the hot layer, bottom layer is cooler and has less smoke in it. That's because of air that hasn't combusted yet. In rooms adjacent to the fully involved fire, temperatures are lower, causing the smoke to descend and creating a uniform soot deposit on all elevations. Upper layer gas deposit shows directions of smoke and heat travel. So line descends lower in corners just because the ventilation patterns are such that the buoyancy just doesn't allow the gases to be pushed out of those corners quite as well. So it also ascends, that line of demarcation ascends at higher ventilation openings. So if you have a line of demarcation and there's a window open, you're actually going to see it go up toward a ventilation open. That's actually a tool you can use because it will point toward possible openings that existed during fire conditions. So another thing to keep in mind, protected areas can indicate the damage was caused by the extreme conditions of the upper layer and not by a fire in that area. So if you're in an area that's all sooty, keeping in mind that if you had a fire condition and that fire was hot, uniformly hot, such as flashover conditions, what would you inevitably have is a situation where you could have extensive damage. And you're going to look for blockages for radiant heat flow. And if you have like a clock or a picture or, any kind of furnishings, those are going to block transmission of energy. So it's just another tool you can use. So this is actually numerically, it shows the relationship between time and heat flux in kilowatts per square meter. You did peak over 20 kilowatts per square meter at that particular location. Typically 20 kilowatts per square meter at the floor is what triggers your flashover conditions. So for whatever reason, this might be a localized fire that wasn't uniform, but then it dips down lower where that transducer was, that sensor continues on under 20 kilowatts per square meter for a few minutes, and then sustains at 20 kilowatts per square meter for another couple minutes. And at that point, it has enough energy that it just explodes. This is your flashover HRR at that location. Within the compartment, it's probably higher, but we're just looking at the location where this transducer reading was. So at that point, it experienced significant, sharp increase in heat flux, which is suggestive of a flashover. So let's just take a look at some forensics, some test fires. You can see this example. There's a lot of rules to follow. In this case, this was a hot fire flashover. The soot deposition and damage is down lower. This is clean burn up on top. So you can just see how the patterns weave. A lot of it has to do with the ventilation patterns. This is the wall opposite. You had air blowing on it, this location. So you had clean burn here. It actually took out any soot down low. This is the sidewall. The center image is the sidewall. It's this wall here. So you didn't have the ventilation and consequently the clean burn. You did a very, very hot upper layer. It radiated down and deposited soot at these locations because that wall was sufficiently cool to create a condensate of that soot. So here's an interesting test. You can see the smoke layer level here. The room, back room was ignited, but that soot, that smoke layer level is extremely hot. And as it lowers over time, you can see it lowering, getting hotter. And then you see down on the floor, the pyrolysis. The pyrolysis is occurring due to that heat exposure on the combustible floor. It ignites. You're at flashover conditions at this point. Here's another example, a different laboratory test. Once again, you see a back room ignited, a smoke layer up high, it lowers. So 4 minutes between these two images, 1 minute between these two images, and you can see how rapid it's this exponential relationship. Once you start lowering that smoke layer and it gets hotter, the reflection and the proximity, the distance changes. The exposure, the transfer of energy accelerates significantly. So you can see at this point, your floor is already on fire. This is well into flashover. Flashover occurred shortly after this, but this is fully involved fire, flashover conditions. Here's a couple references that were used in this. So, hey, appreciate your time. Thank you, and have a good day.